All right, gang, the race is on again. So we have a laboratory to do, and we've got to find the actual speed that something is traveling at the bottom of a ramp as it's rolling, not slipping, versus what it should be doing. So here we go. Here's how we do the lab. So we're going to look at rotational kinetic energy today. It's something that a lot of people don't even think about, but it's actually there. Because if something spins, if a mass is spinning, it's got the ability to do work to something. It can actually impart some work on something and transfer some energy. So a little reminder here, guys. Energy, it is the ability to do work on an object, cause some kind of a change. Couple forms. We've got the ability to do work, which is the potential, and the actual something's actually happening, the kinetic side of things. So we're looking at two kinds of mechanical energy. Potential comes in not just mechanical, but all kinds of different types of energy, whether it's elastic stored energy, gravitational potential energy, all kinds of stuff. Kinetic energy from mechanical things, it's something's actually moving, some mass. Alrighty, guys, let's get more into it. So we've learned about translational kinetic energy. A mass is moving. And what the new thing is rotational kinetic energy. Guys, a disk can be spinning. If the disk is spinning, is the energy stored into that thing. And we can actually use that energy to do work on something else. We could spin a generator with that, make electricity. We could do all kinds of things with that kind of energy. And the author of this suggested a vibrational kinetic energy, kind of like with molecules vibrating your body and the table and the floor, things like that. But in reality, vibrational kinetic energy is it's basically this translational kinetic energy that's just changing directions. And we talk about gas in the air. It's translational kinetic energy. It's the moving mass in the air. It's basically what temperature is based on. The higher the temperature, the higher the kinetic energy of these particles, means they're moving faster. But it's also the rotational kinetic energy of those particles as well, because they can do work on things. They can smack things and make other things spin. So there's more than just one kind of kinetic energy there. But in mechanics, it's not just the translational stuff, it's also this rotational stuff we have to be concerned about. So that's the big lesson today. How do you incorporate the rotational kinetic energy into that? So law of conservation of energy. Energy is always there. We're just doing work to change it from one form of energy to another form of energy. So we can't create or destroy it. We're just doing work to change it from one to another. So, of course, we know that's potential energy sitting up there all by its lonesome, not doing squat, because it can go lower than that because of gravity. It's got some gravitational potential energy. Okay? That's specifically potential energy due to gravity. And it can go down and it could be rolling on the ground there, and that could be a kinetic energy as it rolls on the ground. Not just translational, but also could be rolling or rotational kinetic energy. So not only it can push on something and move something out of the way, it can also roll and cause something else to spin, which is rotational kinetic energy. So we have to, in reality, include both kinds of kinetic energy when something rolls down a ramp. So, whatever we start with, the initial energy we should have the same energy at the end in one form or another. And the example we just looked at is the lab that you guys are going to do. You're going to have to find a couple of different rolly objects. I'd like them to be different shapes, so they're going to be going different speeds at the bottom. But whatever energy you start with, you should end up with at the end. And we're going to keep it easy. So we're going to start with potential energy at the top, a little mgh, mass times your 9.8. You're going to do this on planet Earth, I would think, times some height that you're going to drop across. And in the end, gravity is going to convert all of that potential energy by doing work into translational kinetic energy, means it's moving in one direction, but it's also rotating. So that potential is going to turn in not just to moving in sideways, but it's also into spinning. Some of the energy is stored in just the spin of your rotating object. So the translational kinetic energy, that's the 1/2 mv squared. But when you're rotating, it's not just mv squared. It's the inertia when you're spinning is the I. It's the moment of inertia. There's no I in team, but there is definitely a big fat I in rotational inertia. And that W thing is your angular velocity in radians per second. And just like we squared the velocity, you're going to square that as well. So the addition of both of those two kinds of energy are at the bottom of your rolling object when it rolls without slipping is going to equal your potential at the top. Theoretically, if there's no energy loss to thermal energy because you're rubbing something the wrong way or you're colliding with something. Alrighty, let's keep on rolling. Literally. So moment of inertia, we've talked about this already. I'm going to go kind of quick. So inertia is a tendency to stay at rest if you're at rest, or in motion, stay in motion, and mass is the only factor for that. That's translational inertia. We don't call it translational inertia, we just call it inertia. But when we talk about moment of inertia, that's a fancy term for rotational inertia. It's not just the mass, it's where the mass is located, how it's distributed, how far is it from the point of rotation, and how is it moving about the point of rotation. So it's a little more complicated. So it's a measure of the object's resistance to a change in rotational motion, getting faster or slower. So it's like the idea of the mass, but there's a few more things going on to make the amount of that inertia a little more complicated. So the mass is part of it, but it's also where the mass is located as far as how the thing is spinning. So we have all these different shapes. So the new kid on the block is this one over here. So we just use the hoop thing as all the mass is on the outside. In reality, hoops tend to be kind of thick, and if you want to be spot on, you're at two different radii, so you got to do this little shindig. The first radii plus the second one and blah, blah, blah. We're going to simplify things. We're not going to get that complicated. We're just going to measure to the center of that thing and say close enough. Alrighty? So we're not actually going to use this. There's going to be the example in this PowerPoint. We're not going to use it. So choices that you might use for your lab probably would be something like this, a solid disc if you can find one of those. A hollow disc, which I'm going to call this, they call it a hoop. They call that a hollow cylinder. I'm going to call this the hollow disc. This is what we're going to use. This is what would happen if you spin around it in a weird manner. You're not going to roll that down the ramp. You might roll a basketball down your ramp. So that would be like this, the 2/3 mr squared, where all the mass is on the outside because it's a shell. Or you might have a solid ball, like a ball bearing a marble or something like that. That's a 2/5. A tennis ball would be more like the 2/3 over here. And you're not going to roll this. It doesn't going to roll like that. That's not how things roll. If you roll something like this down your ramp, that's actually this thing over here because you're rolling through the center this way, not through the end this way. So your choices on your lab are probably going to be the solid disc, the hoop-like thing with all the mass on the outside, a solid sphere, or probably the thin spherical shell. Those are going to be probably the ones that you're going to pick. You only have to pick two. You're going to find something in your house. You got to have something that's going to roll down some kind of a ramp. So you're going to have to find two different kind of thingies to roll for your lab. Alrighty. Tangential velocity, that's just your distance traveled per time. Yes, tangential velocity at B1 is greater than A1 because it's at a greater radius. Tangential velocity is a distance traveled per time. Okay? So it's the speed. Tangential velocity is speed. Same thing here. B2 is at a greater radius. It's going faster than what the A2 is if it's tangential velocity. Angular velocity, it's all the same because these are rigid bodies. Every point on either one of these makes the same turns per second. So the angular velocity is the same everywhere. The tangential velocity is not. Alrighty. That was just a little review there. So once again, we're going to look at the potential energy at the top of your lab, and ideally it would be the same as your total kinetic energy at the bottom, not just the energy going in a straight line, but also consider the spin of your object. So you got your 1/2 mv squared, and you got your 1/2 moment of inertia times your angular velocity squared. You're going Greek. Okay? So you might be saying, whew, I Okay, so I have some issues with the lab. I know this is 9.8. I know I'm on Earth. I can find a way to do a height in some kind of unit. I don't have a way to measure the mass, and that's going to make some of this other stuff kind of tricky. Well, I wouldn't be giving you this lab if there's not a way to de-trickify it. So let's go ahead and de-trickify this whole setup. Alrighty, so measure an angular velocity. That's just your turns per second, right? So if it's going slow enough, or if you have a big enough object, you might measure your turns per second, or it might be easier for you just to measure your distance per time to find the actual velocity at the bottom of the ramp, however you want to do this, okay? Angular velocity is a pseudo-vector. It's not really a pseudo-vector. If it's rotating like this, there's that right-hand rule you learned about in the other video, if you watched it, that your hand rotates like this, and that means my thumb would be pointing into the screen. I know it looks like it's pointing out. I'm using the mirror thing on this, I guess, or something. And that means it would be going into the screen, the direction for that. That's not going to make a lot of sense until we get to another week or so into the angular momentum. It might make a little more sense. Don't worry about the direction thing for now. This is kind of a weird thing to do angular velocity. I would just put a theta here, and that's just angle per time in radians. What they're doing is saying that's a rotation, that's a revolution. So if you put a revolution per time to go to radians per second, you got to go 2 pi because it's 2 pi radians in one revolution. I would just put a theta there and do in radians per second, whatever. But this is what we use, okay? This is where the magic happens because you're going to convert basically this W-looking thing into a V. Because remember, your V is the W-looking thing, which is Greek omega times your R. Or, rather than convert, you're going to substitute the V over R, which is your translational velocity or your speed, the speed of the object going sideways, divided by the radius in for the W-looking thing. Okay? So you're going to substitute that in. It's going to make your math a little easier. So it's going to look complicated at first. It's not that big a deal. Alrighty. So there you go. We're going to substitute this V over R in for that in just a moment. And then we'll put whatever we need to in for the I, depending on whether you pick the solid disk, the hoop. We're not going to do this stuff. If you want to, you can, because you'll be more spot on if you got a fat hoop. Yep, that'll work. But if it would me, I would measure to the center and be done with it. Or use your basketball, use your bowling ball on your ramp. Those are another couple ice items you could use. And so there you go. Alrighty, so you're going to start up here with all MGH, no speed. Let it roll down to the bottom, and then you got to find out how fast it's going at the bottom. You're going to calculate first how fast it's going, translational, or just how fast it's moving in a straight line, and then how fast it's spinning in radians per second, and then you're going to actually measure that to see how well they match. Then in your conclusion, you're going to talk about how well they match each other. Alrighty. So the author here has a height of 8 centimeters, it looks like, and there's the radius, 2.5 centimeters of, I guess, every single object the person's using. Of course, it's not a Martian doing the lab on planet Earth there. And here we go.